Hi, welcome back to my channel. So this is a continuation of my previous episode, and I'm still playing with the QRPLabs 10 watts linear amplifier that I have here. It is connected and powered up by a battery. Here you can see the amperage, so the current consumption, and here the voltage of the battery, currently at 12.6 volts. So here I have the amplifier, and the output is going to this attenuator and then is terminated by a 50 ohm load. So basically the output is completely dissipated in it by this thing here. So what I want to investigate now is the input impedance of the amplifier. So let me just, I prepared just one page to explain this quickly. So let me see if I can show you to you just like that. So here we have a source of a signal. It could be my signal generator, or it could be something that produces a low power signal, basically. For example, the AKRF. The AKRF is this device, and its output power is very, very limited, okay? So it needs an amplifier, and this is one of the reasons I bought this amplifier here. Anyway, imagine this is our source, and the source in RF typically has a 50 ohm impedance, okay, an internal impedance that we can imagine like a series resistor inside the generator. Then we have usually a coax connection, so a cable, and this is going inside the input of the amplifier. So now this amplifier will have its own input resistance, which is what I'm going to try to find out here. And it will also have, when it outputs its signal, it will have an output impedance, okay? So but that's not what I'm looking at right now. I'm interested in this input impedance. Because in the datasheet of this amplifier is basically unspecified. So it says that it can vary. It's not 50 ohm, okay? So you should not expect this amplifier to have a 50 ohm impedance, so this is unlikely to be 50 ohm. And the problem with this is the following: when you have a signal that starts at some given impedance, like typically 50 ohm here, it travels through a coax that is also 50 ohm, so the signal is very happy, but at some point it will enter in contact with this Rin resistance, the input resistance of the amp, and depending on the mismatch between this 50 and this Rin, there will be some reflections. So a portion of what comes in will be reflected back, and will go back to the source. So now this is not a problem if the source is an instrument like this, which is designed, you know, to be very robust and handle reflections. But if the source is something more delicate, such as this AKRF here, this can be a problem. The AKRF, if you read the instructions of this device, so it's a very cheap device, so you cannot expect too much in terms of protection, circuits for protecting the output. So it says very clearly in the manual that if the reflection are too high, you can burn the AKRF, okay? So you should not do that. And to calculate the reflection, there is just some simple mathematical formula. So there is a reflection coefficient that basically tells you the percentage of the stuff that is going inside the amp that will be reflected back, okay? And so this percentage can be calculated, is this gamma here. It's simply calculated by this R, which is the input impedance, minus 50, which is the standard 50 ohm impedance of the source and the coax, divided by R plus 50. Okay, so this is a linear coefficient. If you want the logarithmic variant, it's called the return loss, and you calculate by this formula. Okay. Okay. So I have a couple of examples here, just to illustrate this concept with practical numbers. So let's assume the best case scenario when this R input is 50 ohm, which is typically what is desired. Then we get 50 minus 50 equals 0, divided by 100. So the whole thing is 0, right? So in this case, when the R is 50 ohm, we get gamma is 0. meaning that the reflection is 0% of the input, so there is no reflection. Logarithmically, this means that the reflection is minus infinity dB down compared to the input, okay? So basically, that's what this means. And there are two extreme cases. One is where R is 0, so basically here we have a short. In this case, we get minus 50 divided by 50, and that's minus 1. Logarithmically, this becomes a 0. It means that 100% of the signal is going to be reflected back, okay? And the minus is just means a phase shift. That's not important in this discussion. And similarly, if R here it's basically a disconnected circuit, so the resistance is infinity, we get here basically infinity divided by infinity, that's 1. Okay, so basically infinity minus 50 is basically infinity, and similarly infinity plus 50. And so again, we get the full reflection. And then we have other more realistic cases. For example, if R is 75 ohm, 20% gamma is a 0.2 or 20%, and in terms of this means that basically the reflection is 14 dB down compared to the input. If R is 270 ohm, well, we have 68% or 0.68, gamma 0 is 0.68, and this means that the reflection is only 3.25 dB down compared to the input. And then we have other cases, so like if R is very high, 1 kilo ohm, then gamma becomes 90%, 0.9, and the reflection is only 0.8 dB down compared to the input. Okay, so here I have an instrument that you probably know from other videos as something quite cheap that you can buy on AliExpress and this type of thing, is the Nano VNA. And if you're interested, I did other videos already about the Nano VNA, like in this episode, so have a look if you want to know more details. But here basically, so at the moment we are looking at what happens when well, there is nothing at the output of the Nano VNA, so basically we have the R here is infinity, and indeed I don't know if you can see, but the return loss written there is 0 dB. Okay, so we are in this situation here. Okay, so let me try now to connect just to see 50 ohm load that I have here. Okay, and now well, basically, as you can see, the return loss has gone down basically to the bottom of the Nano VNA. Okay, so that's with the idea that as we had here with 50 ohm, we get basically minus infinity. Okay, so we are at the very bottom of the basically the sensitivity of the Nano VNA. Here I have just to make other tests, just to see if the theory matches the practice. So this is a 70 ohm resistance that I have here. So let me try it. I'm going to connect it here and see the result. And so let's see the result. If you can see, is that the reflections, the return loss, hopefully it will focus at some point. Anyway, it says minus 14.19. Yeah, now you see minus 14, and that is pretty close to what the theory predicted. Okay, and finally here I have that's why I chose this this specific number. I have just one resistor, just to show you that this is really working for all cases. It was just a random resistor I had on the desk. So let me make the experiment, and now with this, this is a 270 ohm resistor, and indeed, let's see if I can somehow focus. Anyway, it says minus 3.22. Sorry, this camera is not really good at focusing, but anyway, so it's a bit of a fail, but it says, believe me, it says minus 3.2. There is no way I can, oh, maybe. Anyway, you cannot see that, but so anyway, this is again incredibly close to the theory. So 3.22 here, the theory predicted 3.25. Okay, so I'm now going to just let's see, connect power on the amplifier, and we will discover the input impedance of the amplifier using the nano VNA. So let me do that, and then I will power on the amplifier, which got disconnected by accident. And so let's start. Okay, the amplifier is working, and here I can show you the result on the nano VNA if it can focus. Okay, so let me see if you can see. Anyway, unfortunately, as you can see anyway, even if the focus is not perfect, the return loss is very high here. Okay, it says at the moment minus 2.3 dB of return loss, and here where it says the impedance, it says about 280 ohm. So this is really, as you can see, it's pretty flat across all the spectrum that I'm measuring. I'm starting at 1.8 megahertz and ending at 30 megahertz. So this is all basically the spectrum of frequencies that this amplifier is supposed to work on. And so yeah, the reflection is very high. Okay. If I show you, let me go here. Many people, if you are a ham radio operator, you're probably more used, instead of the return loss, to this SWR coefficient. Okay, so there is a one-to-one correspondence between return loss and SWR. For me, the return loss is more clear what it means, but anyway, it's typically considered that an acceptable return loss, SWR, must be at most 1.5. which means about 14 return loss. Okay, so here we are in a much worse situation. Let me see if I can see in this conversion table where we are, about 2.3 dB, and so we are here. So the SWR of this, if we want to express the input impedance of this amplifier in terms of SWR, it would be 7.6. So it's very high, unfortunately. I was hoping for something better, to be honest. But okay, it's not the end of the world. It definitely means that I cannot directly plug the HRF like it is right now. There are two solutions, basically, to this problem. One solution, let me zoom out slightly. One solution is to basically plug another resistance in parallel with the input resistance of the amp in such a way that the parallel resistance of these two things will become 50 ohm. Okay, so that's something you can do by soldering now things on this amplifier. Another simpler solution, if you have an attenuator, is to plug an attenuator here. For example, let's say a 6 dB attenuator. The idea is that no matter what the reflection here are, so the signal that's come out of the source, here it gets attenuated by 60 dB, and when there are reflections, even if they are 100%, they will be attenuated by another 60 dB. Okay, so the source will always see the reflection at most at minus 12 dB down, which is acceptable. Okay, so that's a solution, but of course it's not great. So let me try with this other solution here. So let me see. I have here, I found it before. So I have a resistor, which is about let's see if I have a resistor which is 55 ohm. okay? And the fact is that if you put in parallel 280, which is the input impedance of this amplifier, with 55 ohm, you get something like 48. I made earlier the calculations. 48 ohm, so slightly below 50, but okay. And so let me show you what happens if basically I put this resistor in parallel with the input resistance of the amplifier. So let me try to do that. So as you can see now, hopefully, the return loss has gone down quite dramatically. Now it says, so let me try to zoom in better because it's interesting. I mean, okay, so after some fighting with the camera, this is the best I could achieve. So I hope you can see that now, yeah, the amplifier is set at 14 megahertz. It's reading 284 ohm, and it has a return loss of minus 2.29. Okay, so look at what happens when I short this. I simply put a resistor in parallel here with the input. So manually, so that's not an ideal thing to do, but just to check what happens. So yeah, okay, so as you can see now, if so the return loss now is reading minus 30, which is excellent, and impedance here is 14.5. So the situation is greatly improved for sure. Of course, this will have some consequences that I will have to check. So let me remove the resistor. So anyway, that's a way to solve to fix the problem. And so since my intended application for this amplifier is indeed to experiment with this HRF, I will probably do this modification and expect some loss at the level of amplification. So probably it will lose some amplifying power, but I prefer to have a better input impedance. Hi, I couldn't resist, so I did it immediately. So as you can see here, I've soldered directly this resistor at the input. So now the impedance is good. It's around 50 ohm. I think it's 48.5 at 14 megahertz, which is the frequency I'm considering now. And so here I'm basically, so again, focusing problem, but anyway, so voltage, amperage, the amplifier is amplifying, and from the input generator I'm generating a signal, as you can see, hopefully. So the signal is at 14 megahertz with a 4 dBm power, and here this is the output is going after. So basically, if originally the amplifier was amplifying 26 dB, and so it means that 4 plus 26 30, and since here I have a 30 dB output, in my previous video I showed that I was getting something around 0 dB of inside the oscilloscope, right? So for an input, 26 in amplification, so 30 minus 30 equals 0, right? And so now I'm getting a signal, and if I look at the FFT, so let me try to zoom there. Hopefully you can see we have 5 dB per division, and so we are at minus 3, okay? Over there, hopefully you can see. So this means that now the amplifier has lost 3 dB of amplification, and it's only amplifying plus 23 dB, which, depending on your situation, it could be a good compromise or not. Since I want to experiment with the HRF, I prefer to have a better input resistance and a worse gain. But if you have other devices, like if you're generating a signal for something that can handle reflections, this is probably not, you don't really care about the reflections, so you prefer more gain. So anyway, this is yeah, this is what I wanted to test. I'm pretty happy with the result anyway. And then I will have to look at the output resistance, but I will do that in another video. See you. Bye bye.